So it is my great pleasure to introduce the first speaker of today, Professor Joanna Kułaga-Przymus, the professor from the University of Copernicus, Toruń, Department of Mathematics and Informatics. Her specialty is ergodic theory. We heard about it a bit yesterday. Her interests especially involve elements of number theory. Probably we'll hear about that. Recently, her main point of research is the Sarnak conjecture, which exactly involves the ergodic theory and elements of number theory. This is just the statement how deterministic, how rather random are deterministic sequences like Möbius, for example, Möbius sequence. For her work, Joanna Kułaga-Przymus received many prizes, in particular the Polish Mathematical Society prize for young mathematicians, and also the Kuratowski Prize, which is organized, as was mentioned before, jointly by Polish Mathematical Society and Institute of Mathematics, Polish Academy of Sciences. She was on the jury of the Kuratowski Prize for some time, and right now she's a member of jury for the International Banach Prize for PhD dissertations. She's also a member of the Young Academy. This is the Young Academy, so to speak, the baby academy of a Polish Academy of Sciences. The Zoom is yours, Joanna.
Okay, thank you very much. So thank you for the invitation, for the introduction. It's a pleasure to give a talk here. I regret not being with you in person, but sometimes life brings surprises, so this is the most we can do. So let's start. I will be talking about sets of multiples and various aspects of these sets. So what are these guys? Our object for this talk is as follows. So you pick your favorite subset of natural numbers. It can be finite, it can be infinite. Of course, in the infinite case, many more interesting things will happen, but finite case is also admitted. And when you have this set B, you build on it the set of all multiples. So this is the set MB in here. And its complement, FB, is called the B3 set. So it looks more or less like this. So here there is 0, 1, 2, and so on. And when you pick a B, you're putting arithmetic progressions like this on the integer line, and then you have another B in the set. So you put elements along this other arithmetic progressions, and you get your set of multiples. And it is convenient to think about sets of multiples in terms of these unions of arithmetic progressions. That's why I'm drawing this picture. Okay, so a few basic remarks. So first of all, if you have a set of integers which is closed under taking multiples, then it is its own set of multiples. So one can say, one can notice that you can produce the same set of multiples starting from many different B's. So this might be a little bit inconvenient. That's why we introduce the notion of primitive sets. So we say that B is primitive if whenever we have two elements in the set such that one of them divides the other, then actually they're the same element. So we don't want to have in our set, for example, 2 and 4. 4 is redundant from the perspective of sets of multiples. And for any set B, there exists a unique primitive set, which I will denote by B prime, which produces the same set of multiples. So you can think for a second or a minute about this. So this star will always denote in my talk a small exercise. So if you get lost, you can keep thinking about these things or later. Okay, so examples. So first of all, if 1 is in B, then the set of multiples is everything, and its complement, the B3 set, is the empty set. So this is not really interesting. We usually don't want 1 to belong to B, because we won't see any interesting properties or behaviors. So what about more complicated examples? So let's take as B the set of squares of all primes. Then the corresponding B3 set are so-called square-free integers, integers that are not divisible by any square of a prime. And if you think about this square-free integers set, if you take its characteristic function, then it will be actually the same as the square of the Möbius function. So actually not precisely the square of the Möbius function, but the square of its symmetric extension. So the Möbius function is arithmetic function defined on integers, on natural numbers, and taking values -1, 0, and 1. The value at 1 is 1. And if you have a product of k distinct primes, you put -1 to k, and otherwise you put 0. So it looks like this. At 0, we have a 0. Then 2 is a prime, its square is 4. So at 4 we have a 0, and then we put zeros along this arithmetic progression. Then somewhere there is 9. So we will have arithmetic progressions of zeros like this, and so on. And the rest, what remains after this procedure for the Möbius function, is filled, or for the symmetric extension of the Möbius function, is filled with 1s and -1s. And for the square, for the characteristic function of square-free integers, we'll just see 1s between these zeros. So you can think about this characteristic function as 0-1 sequences. Okay, so let me erase this because more examples will come. Okay, so of course, this is not the only possibility for our B. We can start with whatever we want, but if we want to produce something interesting, it's useful to assume that B is infinite, pairwise coprime, and there are not too many numbers in our set B, which is expressed by the assumption that the series of reciprocals of B is summable. If these conditions are satisfied, we say that B is R dash. And this is actually like the simplest non-trivial situation where really something interesting will be going on. And what kinds of examples do we have here? We have this square-free case, but you can also put k powers of prime numbers for k at least 2, and well, many more. So you can produce easily many examples like this. You just have to make sure that you have an infinite set that is pairwise coprime, and if you have put too many numbers, you can just erase some of them to get more examples. Okay, so let's go to something classical. Abundant numbers. So we say that n is abundant if the sum of its divisor exceeds 2n. This set is closed under taking multiples. This is not hard to check. It's like one line. And A3 numbers are precisely perfect numbers and deficient numbers. So the union of perfect and deficient numbers is an example of a B3 set. And then you can think a bit what happens just for deficient numbers. Okay, so here I have written the first few members of the set of abundant numbers. I'm not going to read that. And I said before that you can always find a primitive set that produces the same set of multiples. And the answer to that exercise from the previous slide is just that you have to look at your set, in this case A, and you remove whatever you see, whatever is the multiple of something that you had previously. So we need to remove 24 because it's a multiple of 12. We have to remove 36 because it's a multiple of 12, and then you have to remove 40 because it's a multiple of 20, and so on. So one line below A, you have this primitive set A prim. So this is 12, 18, 20, 30, and so on. And you can easily notice that this set is not pairwise coprime. So this doesn't fall into the previous scheme. However, its series of reciprocals is summable. We will see an argument for this later. So this is just to show you that this R' case doesn't cover everything, and there are even classical examples like this that are different. Okay, so what can we say about these sets? So the two basic tools are the natural and logarithmic density. So natural density is a way of describing how large a subset of integers or natural numbers is. So for subsets of natural numbers, we look at, we check how many elements of our set we see in the window from 1 to n, we divide by n, and we take the limit. So if this quantity exists, we call this the natural density of A. If it doesn't exist, we just use the lower and upper limit to define the lower and upper density. And we can do the same with a little bit different averaging to get logarithmic density. So again, we check in the window from 1 to n if an element, so here I denoted by k, it's not writing, it's sitting there. Jestem zajęta. Nie mogę teraz. Nie mogę. If the element is sitting there, we put there, we add 1 over k. So we sum over all such elements. And since the sum of 1 over k for k from 1 to n is roughly speaking logarithm of n, we average by dividing by logarithm of n. And again, if this quantity exists, we get, we call it logarithmic density. And if it doesn't, we speak of lower and upper logarithmic density. So when I started talking about these two types of densities, I said first that it's defined for sets of integers. So all our sets are symmetric with respect to the origin, with respect to 0. So we just take, will be thinking about densities of this right part of our set. So equivalently, one could look at the window from minus n to n, but it's just easier to deal with subsets of natural numbers. And there are some basic relations between these quantities. So natural lower density is always the smallest, natural upper density is always the largest of them, and then in the middle we have lower and upper logarithmic density. This can be proved, for example, via Abel summation formula, but I have seen more proofs of this. You can easily find that, or you can try to do this yourself using, for example, Abel summation formula. Okay, so the very natural question asked already in the 1930s by Besselhagen, well, 1929 to be precise, was whether the natural density of the set of abundant numbers exists. It was answered independently by Davenport, Erdős, and Chaula. The answer is yes. So then you can ask if the same is true for any set of multiples or any B-free set. And Bezikowicz was able to produce examples where this fails. How did he do this? Well, the basic idea of his construction was to take intervals from tk to tk, where tk is some rapidly increasing sequence, and then produce a set of multiples out of it. So for convenience, I'm just taking this primitivization of this set. So this will produce the same set of multiples. And if tk is growing fast enough, then the upper density of the set of multiples will be at least 1/2, and the lower density will be as small as you want. Then in 1936, Davenport and Erdős proved that even though natural density might not exist, the lower density and logarithmic density will agree. So in particular, logarithmic density of sets of multiples or B-free sets always exists, and actually more than that. So if your set B is infinite, you can approximate this quantity, the logarithmic density of the set of multiples, by densities of periodic sets of multiples produced by truncated set B. So we just take all members of B that are smaller than K. This is our BK. Since this is periodic, it has natural density, and these numbers approximate the logarithmic density. And there is also a very technical criterion when the density of the set of multiples exists. I don't want to go into details here. This is sometimes useful to know that there is a criterion, but it's painful to use it. So just a small note on the margin that there is such a thing. Okay, so what more can we say? I need a definition. So if both n and n plus 2 are square free, we'll call them twin square free integers, like twin primes. And the natural question is whether there are infinitely many pairs of twin square free integers. And if we ask this, you can also ask, okay, so what about all B-free sets? So in particular, what about the union of perfect and deficient numbers or deficient numbers? So how to approach this? I will need some notions from dynamics. So let X be the set of all two-sided 0-1 sequences. I will also need cylinder sets. So cylinder sets are sets of two-sided sequences where, oh, that's not a straight line, where some positions are fixed. So for example, I pick this place, this place, this place. I want to see 1 here, 0 here, 1 here, and I don't care what I see elsewhere. So okay, so these are cylinder sets, general cylinder sets, and what I wrote here are cylinder sets where I just defined the first K position. So actually, I didn't want it red. I wanted it yellow. So I want this. And the cylinder sets are Klopen, and they form a base of the product topology.
Sorry, just
product. Sorry.
probably this index I should run through all integers, yes, not necessarily positive.
Okay, it would be okay if it runs from minus k to k, but you can also think about cylinder sets where some positions are fixed, not necessarily the consecutive ones. I mean, both
Yes.
approaches are okay from my perspective.
Yes, but in the first line, the first line, I is positive. It not need to be positive, yes?
It doesn't need to be positive, but you can just pick like minus 7, 0, and 8 and fix these positions. This can also be called a cylinder set.
Okay,
I mean, because here I runs from 1 to k. So these are positions 1 to up to k. And you don't necessarily need to pick consecutive positions. I mean, so
you also need negative indices.
Yes, I definitely need negative. So it would be okay if I wrote, okay, I need to change my tool. This goes here. If this was minus k, this would be better. Okay, so then positions from minus k to k would be fixed. These sets also form a base of product topology. If I admit more cylinder sets where like a finite number of positions are fixed, this is also okay. Is this fine now?
Yes, yes, yes. Thank you.
Okay. So product topology is metrizable. You can write down the metric explicitly, and you should think about this in the following way. So points x and y. So these two-sided 0-1 sequences are close to each other if they agree in window from minus n to n for large n. Okay, I will also need some dynamics. So let sigma stand for the left shift. This means that I just shift my 0-1 sequence by one position to the left. So I wrote down the formula for this, but it's easier just to visualize this by just, by picking your sequence and shifting it physically. Okay, the set of all shifts of a given sequence is called the orbit of this sequence. And now any closed sigma invariant, so shift invariant subset of all 0-1 sequences will be called a subshift. There are many examples of subshifts. So for example, you can just take all two-sided 0-1 sequences. You can just take 1 point, just 1, 1, 1, 1, 1, or only zeros. You can take the orbit of any periodic point, or you can take the orbit closure of any point. The orbit is already invariant under the shift, and to make it close, we take the closure. It doesn't destroy the property of being invariant under the shift. So what can we say about this orbit closure? What will be crucial for us is how the elements on the orbit closure of X look like. So Y is in the orbit closure of X if and only if any block appearing in Y appears in X. So you don't see on Y any block that would not appear from X. This gives you the family of X gives you the family of allowable blocks. And this can be justified using the notion of product topology. Okay, so how is this related to B-free sets? Given set B, we have this corresponding set of multiples and set of B-free integers. And I already was telling you about these arithmetic progressions of zeros and ones. And this is what will appear here all the time. That's why I'm giving it a letter. So eta will be the characteristic function of B-free integers. This is a two-sided 0-1 sequence. Or it can be thought about two-sided 0-1 sequence. By definition, it's a function from z to 0-1. So yes, it is a sequence. And now we take its orbit closure, so x eta. This is called the B-free subshift. This is our main player in this talk. If B is R-, so if it's pairwise coprime infinite with summable series of reciprocals, then it turns out that the B-free subshift is hereditary. This means that if some sequence is in this subshift and you take something, oh, this is missing here, take something smaller coordinate-wise. So if y is in here, x is in x eta, and y is smaller or equal than x, then y is in x eta. So you are allowed to replace ones by zeros in sequences, and you stay in the subshift. But this is not always the case. This is true in the R- case, also beyond, but not always. So in case the B-free subshift is not hereditary, then one sometimes considers the hereditary closure of the B-free subshift. I denoted by this tilde. This is the smallest hereditary subshift containing x eta, and it's easy to construct this. You just take all sequences that are in x eta and you add all possible sequences after this procedure of replacing ones by zeros. And then there is the third interesting player in this game, also very important one. This is the B-admissible subshift. So what are its elements? These are, again, two-sided 0-1 sequences. And we look at their support modulo B for each B. So we want at least one residue class to be missing in the support of our sequence for each B. And if you want to see it on the picture, it means that for each B, we will see an arithmetic progression of 0 with difference B, but it is not necessarily placed at 0. It can be moved to the left or to the right. So when I was writing eta, then I was placing these arithmetic progressions of zeros at the origin, and in the B-admissible subshift then can be moved to the right or to the left. So actually I just justified why x eta is sitting in the admissible subshift. So the B-free subshift is a subset of B-admissible subshift. And since the B-admissible subshift is hereditary, you can think for a second why, we get these two inclusions. So x eta is sitting in its hereditary closure, and its hereditary closure is sitting in the admissible subshift. Sometimes all of them agree. So this happens if B is R. Sometimes they don't agree. So I don't want to go into details here, but there are many examples where one of these equalities fails, the other not, and so on. Okay, so actually I already touched this because we talked about subshift, but I want to talk now about general notions from topological and measure theoretic dynamics. So if X is a compact metric space and T is a homomorphism of X, we say that XT is a topological dynamical system. So for example, subshifts are sitting here. And now I want to pass to measure theoretic dynamics, which means that I want to see measures. So by M of X, I will denote the set of all Borel probability measures on X. And some of them are T-invariant, some of them are not. So what does it mean to be T-invariant? A T-invariant measure is a measure that is preserved when we take pre-images of any Borel set. And the set of those measures will be denoted by M of xt. And now if the only invariant sets, So the sets that are not moved by t are sets of measures 0 or 1. We say that our measure is ergodic. So these are kind of special measures. Sometimes we will just say that t is ergodic if the measure is clear from the context. And I will denote it by me of xt. And now for any invariant measure for our topological system, the triple xt mu is called a measure theoretic dynamical system. And there are many examples. So we can take the full 0-1 shift with a measure concentrated or equally distributed on a periodic orbit. We can take the full shift with any Bernoulli measure. There are many more. We'll see some in a moment. Okay, so some classical results about invariant measures. So just that you know what we are dealing with. So first of all, the set of invariant measures is always non-empty. That's the first thing. So you could ask whether we can always produce a measure theoretic system from a topological system. Yes, we can. The second thing is that the set of ergodic measures is not empty. This is deeper, the proof is more difficult. And what is important to know about this is that ergodic measures can be thought of as extreme point of all invariant measures. And then one can use Krein-Milman theorem to complete this proof. That's the second important result. And the third result is the ergodic decomposition theorem. I'm not writing it here in a very concrete form. I'm just giving you very general statement. So any invariant measure is a general convex combination of ergodic measures. So there are quite a few formalities to write it down. There are some integrals involved, but you can just think about this as the fact that you can produce all other measures from ergodic measures. So basically, if you want to learn something about invariant measures of a topological system, you start with describing ergodic measures, and then the rest might come automatically. Okay, one more thing, generic points. Okay, so on the set of all t invariant measures, we have weak star topology. So nu n converges to nu if the integrals of continuous functions converge. And for subshifts, it suffices to check this convergence for characteristic functions of blocks. So in other words, for any cylinder, we just have to check that the measures of these cylinders for nu n converge to the measures for nu. Again, there is the same mistake for the cylinders. No, here it suffices. So these are not all cylinders, but for this slide, this is okay to stick to positive coordinates. So cylinder sets are Klopen, their characteristic functions are continuous, and they're linearly dense. So that's why we can just stick to them in here. And now, given a point in our topological dynamical system, we can consider the empirical measures. So we look at the average of Dirac deltas at the consecutive points of the orbit of X. And if this sequence converges to some measure nu, we say that X is generic point for nu. If this happens along a subsequence nk, then we say that X is quasi-generic. Okay, this is pretty general. Let's interpret this for subshifts. So for subshifts, X is generic if and only if the frequencies of blocks on X exist. So this is your point X. Okay, this is the origin. Okay, and then you take a window from 1 to n. And then you're checking, okay, your cylinder C has some length. So we take the limit as n tends to infinity. So I can think of n as of being much larger than the length of my C. So suppose C is 0, 1, 0. So I'm checking, do I see this block here? Then I go one position further and then check, do I see, this starts with 0. Do I see this block here? And so on. And I count how many times I see it on X from position 1 to n. I average by n, and I take the limit. If this always exists, then X is generic. Okay, so already in 1930s, Mirsky showed that the frequency of all 0, 1 blocks on the square of the Möbius function, so in the square-free case on eta, exists. So in other words, the square of the Möbius function is a generic point for some shift invariant measures. Okay, so let's do something more general. So let's be R dash. So infinite pairwise coprime and summable series of reciprocals. Then the characteristic function of B free and integers is a generic point. We call the limiting measure the Mirsky measure. It is ergodic and it has full support. So this means that the frequency of any block appearing on eta is positive. So not only any block appears infinitely often, but it will appear with positive frequency. And now, since in the R dash case, all the three subshifts that I defined before are equal, so in particular, the B-free subshift and B-admissible subshift are equal, it follows that any admissible block appears on eta with positive frequency. So in particular, infinitely many times. I'm speaking about admissible blocks here. Before we had admissible sequences. So this is the same. So instead of taking the support of the sequence, I am just taking the support of this block. And now if 1 is not in B, then 1, 0, 1 is always admissible. So it will appear on eta infinitely many times. So this means that the answer to our question about pairs of about twin square-free integers is positive, because this block 1, 0, 1 will appear on mu squared infinitely often. Okay, so let's go further. So I told you from the beginning that there are many examples of sets of multiples, and they can behave differently. So for example, we have this notion of heredity, and sometimes B-free subshifts are hereditary, sometimes are not. So this is why it is useful to define some basic classes of sets B. So first of all, B is Bezikovich whenever the density of the corresponding set of multiples exists. Then B is thin if the series of reciprocals is summable. B is R dash. We already had this if B is infinite pairwise coprime and thin. So for example, this holds for B being the square of primes. So in this case, the density of FB is 6 over pi squared. This has been known for a long time now, like from the 1930s, or maybe even earlier, I don't know. Then we have something like on the other end, something that behaves completely differently. We have Berendt sets. We say that B is Berendt if the density of the set of multiples is 1. So for example, if you take a subset of primes with non-summable series of reciprocals, you will be in this situation. And the last property is so-called tautness. So when I started this talk, I told you that some numbers are redundant in set B. Like if you have 2 and 4, then you can throw away 4 and nothing bad will happen. And then I told sets of multiples always have logarithmic density. So tautness means that each element is kind of important from the point of view of logarithmic density. So if you remove one element from your set B, then the logarithmic density will drop. And this is equivalent to not containing any rescaled copies of Barron sets. And there are various relations between these classes. Okay, let me skip this. It's not so straightforward. There are inclusions, overlaps, and so on. Okay, I promised you the proof why for primitive abundant numbers the series of reciprocals is summable. But let me skip this too. Let's assume that we already know this. And if you know this, and if you also know that for the taut sets Mirsky measure has full support, then you can conclude that there are infinitely many twin numbers in the union of perfect and deficient numbers. Okay, so what about deficient numbers only? I will be skipping proofs here too, but if you know that the density of perfect numbers is 0, then you can easily conclude that there are infinitely many twin deficient numbers. To be honest, I don't know what's the earliest proof of this. I believe it must have been known for ages that there are infinitely many twin deficient numbers, but I couldn't find any references. All right, so let us go to something more challenging. So the first observation will be that you can see primes as B-free sets. So if B is the set consisting of all elements of the form P times Q, where P and Q are primes, then the set of B-free numbers will be plus minus primes and, well, plus minus 1. Okay, that's one thing. The other thing is the subshift of primes. So you can just put ones when you see a prime, and you can put zeros elsewhere, and you can take its orbit closure. So this is called the subshift of primes. And now the characteristic function of primes and eta. So eta corresponds to this. They differ only at 2 positions. So basically, if we describe the some properties of B-free subshift, in this case, we describe properties of the subshift of primes. So to be more precise, these 2 subshifts will be conjugated. And this has to do with the fact that both the characteristic function of primes and eta are isolated points, and they differ only at finitely many positions. Yeah, I'm slow, so let me skip the proof too. Just this is just a remark that should convince you that there is no difference whether we study the subshift of primes or we study the B-free subshift in this case. Okay, so clearly this set B is a Barron set as the density of primes is 0. This follows immediately by the prime number theorem, but there are also some elementary proofs. So you can look for that and you will easily find this. But actually we have more than that. So not only the density of primes is 0, but also the upper Banach density of primes is 0. And by upper Banach density, I mean the density in sliding windows. So when I was defining natural density, we were checking how many elements on average we see in such frames. And now I'm allowed to put my frame wherever I want. And again, I'm checking how many elements I see. I'm taking the supremum over all m and then the upper limit with respect to n. So this is the upper Banach density. And it is easy to deduce that the upper Banach density of primes is positive. So let me do at least one of these proofs. So the upper Banach density of P is equal to this. So this is just the definition. And now, since primes are basically the B-free integers for this B written at the top of the slide, I can approximate this from below by this truncated set BK. But this for this truncated set BK, the set of BK-free integers is periodic, so its natural density exists. And Davenport and Erdős showed that this converges to the upper density of B-free integers, but this is the upper density of primes. But the upper density of primes is just the density of primes. This is 0. Okay, but the twin prime conjecture, whether there are infinitely many primes, is still open. So we were able to prove that there are infinitely many twin square-free integers, but we really don't know whether there are infinitely many twin primes. So maybe there is a dynamical reason for this. So why the approach that works in the Erdős case or for Todd sets fails here? Let me try to explain this. Okay, so we need to learn a bit more about invariant measures on orbit closures. So let's start with ergodic measure theoretical dynamical systems. So you have this topological dynamical system, for example, a subshift, and there is some invariant measure sitting there. Birkhoff ergodic theorem says that for any function that is in L1, space averages, so this, what I have written on the left-hand side or here, I mean, these are really the same. So, okay, let's look at this middle part. I'm looking at the values of f along the orbit of k, and I'm averaging this. So this converges to the integral of f. And I can rewrite it in terms of integrals of f with respect to these empirical measures. So this converges for almost every x. And since I have rewritten it like this, you can see that this means that almost every point is generic for this measure mu. So
excuse me, just for a moment, if you could go back to the previous slide.
Yeah.
I believe that the direction of this inequality should be the opposite, yes?
Yes, there is a mistake here. Okay, so the heuristic still works, but there are less. Yeah, but I want this to be less.
Yes.
Yes, that's fine. Yeah, I was scared for a second that the proof doesn't work. That's correct. Yeah, this should be like this. I agree. Thank you. If you truncate your set B, you will get more free numbers because there are less restrictions, less divisibility restrictions.
Thank you.
Okay, thank you for this remark. Okay, so we have Birkhoff ergodic theorem that tells us that actually almost every point is generic for an ergodic measure. And now if we look at orbit closures, so let me remind you, the orbit closure is just the closure of alt. So for subshifts, the orbit closure is just the closure of all shifts of my element. And now Y is in the orbit closure if and only if any block appearing in Y appears in X. So if I want to understand ergodic measures on the orbit closure of some element, of some sequence, I can try to understand the generic points of these ergodic measures. And these generic points, since they are in my subshift, they are built from blocks coming from my X. So these blocks are located somewhere. So this is my X, and these blocks are somewhere here. Okay, that was X. And this is how I build my generic point Y. So if I want to understand the frequency of blocks on Y, I actually need to understand the frequency of blocks in these sliding windows on X. So in other words, the set of ergodic measures in the orbit closure of X in the subshift is the set of all such limits. Mk and Nk. So Nk goes to infinity and Mk can jump. So whenever this limit exists, I put the limit measure in the set. Okay, let me put inclusion here for safety. We might produce some non-ergodic measures as well in this way, yeah. Okay, so we have understood how to look for invariant measures on orbit closures. And since the upper Banach density of primes is 0, it follows that all the frequencies of all blocks in sliding windows will equal to 0, no matter how we choose Mk and Nk. So this means that this subshift has only one invariant measure. This is the Dirac delta at the all 0 sequence. So this means that to study, well, this B3 subshift or the subshift of primes, we are left with tools coming only from topological dynamics. So what kind of questions can we ask? What so what is approachable with dynamical tools? Let's look at this. So one of the basic questions for whatever object you have is how large it is, right? So we can ask whether the subshift of primes is uncountable. A small remark, an arbitrary admissible subshift always is uncountable. So it suffices to find a point there with infinite support. And then you can replace ones by zeros to get an uncountable set. So if B is infinite, then you can just take such products. It's easy to check that it will be B admissible, of course, is infinite. And if B is finite, a modification of this set works. Okay, let me go to famous conjectures. So first of all, we have prime k-tuples conjecture. This says that if a set A1 up to AK is P admissible, then for infinitely many n's, we will see this pattern n A1 up to AK on primes. Okay, maybe let me draw this. So I have like A1 here, A2 here, maybe A3 here, and so on. I check whether it's P admissible. So I look at the support modulo each prime. And the conjecture says that it will appear on primes infinitely many times. So all these red numbers will be prime for infinitely many n's. It is not hard to see that if set A1 up to AK is not P admissible, then this can happen only finitely many times. So this is, well, this can be treated as an exercise. So let me skip this. All right. it is also not so hard to see that prime k-tuples conjecture is equivalent to this inclusion. So if we knew that we can remove this tilde, then we would be happy, because any admissible subshift is uncountable. This is an admissible subshift, a p-admissible subshift. So this would be uncountable, and therefore this. But there is unfortunately this tilde in here. So maybe there is a way to get rid of it. Okay, I'm skipping the proof. We have another famous conjecture.
Sorry,
Yes?
I forgot what eta 2 is.
Eta 2 is eta for this B, P, Q. So you produce eta. Well, this is 2 because this is a product of 2 primes. That's the notation. This is eta 2. So eta 2 is basically the characteristic function of primes. So not exactly, but more or less. Okay, the prime k-tuples conjecture is deep. The translation to this inclusion is not deep. This is just understanding what these objects are. You have to get used to them, but when you think for a while, you can easily do that yourself. Okay, we have the second famous conjecture. This is Dixon's conjecture. Since I'm slowly running out of time, so when did we start? How much time do I have?
Still 10 minutes. Because
fantastic. So Dixon's conjecture is a generalization of this previous prime k-tuples conjecture. So there is a condition here, a non-divisibility condition that generalizes this p-admissibility, and the conclusion is more or less the same. So there are infinitely many n such that, okay, such expressions give you primes for infinitely many n's. Okay, so I already said that this is a generalization. This is really easy to see. And so, for example, the set 0, 2 is p-admissible. So in this case, we boil it down even to a twin prime conjecture. Okay, so how is this related to what we are doing? So Professor Schinzel pointed out that actually Dixon's conjecture implies the following. So if A1 up to nk are between -1 and n, and the set A1 up to ak is p-admissible, then for infinitely many x, if you look at primes in interval x minus n to xn, then primes in this interval will be exactly the shifts of these numbers. So prime k-tuples conjecture tells you, okay, let me write this, not draw this. Prime k-tuples conjecture will tell you that the shifts of these numbers are prime. And in this remark, the difference is that what is in between is necessarily composite. So we not only know that certain shifts of something are primes, but we know what is happening in between. And then if you look at this carefully, you will see that we can exactly drop the tilde above x eta 2. So in particular, this means that this B-free subshift x eta 2 is uncountable, as this p-admissible subshift is uncountable. And by the conjugacy of x eta 2 and the subshift of primes, also the subshift of primes is uncountable. So we have a conditional proof of uncountability of the subshift of primes. Okay, there has been a lot of progress here recently. there is an unconditional proof as well. So this is the story. So in 2015, Maynard showed the following. So if you have a finite p-admissible set of size n, then this set has a subset of size, well, more or less log n. So you can just think of it as not removing everything from your set A. And the subset will appear on primes infinitely many times. There exists infinitely many k such that k plus a prime sits in primes. And then in 2023, Tao and Ziegler proved the following. Now we will have infinite p-admissible sets. So if A is infinite and p-admissible, then there exists an infinite subset A prime such that the characteristic function of the set A prime sits in the subsheaf of primes. So in particular, this means that any finite subset of this A prime will appear on primes infinitely many times. So their result is kind of infinite version of Maynard's theorem, and even better because we have this infinite, the characteristic function of this infinite subset A prime sitting in the subsheaf of primes. So the consequence of this is the following. For any infinite p-admissible set A, the following set is uncountable. So what is this set F? This is the set of all subsets B sitting in A, such that B is infinite, and the characteristic function of B is in the subsheaf of primes. So in particular, the subsheaf of primes is uncountable. So all these characteristic functions of B's from F sit here. So this suffices to prove uncountability. So how do we do this? This is actually not so difficult once we have this. So this is like the deepest part. The corollary is easier, and I think I still have 4 minutes, and let me show you that. So suppose this set F is countable. So we have B1, B2, and so on, and we write down the elements of each of these sets. And we consider set B defined as follows. So B1 will be the second element of capital B1. B2 will be some element of capital B2. Which element? Well, an element large enough. And by large enough, I mean that this index I2 is at least 3, and that what I get is larger from what I had in the previous step. And I can continue this procedure inductively. So Bn will be some element from capital Bn, which is large enough. And by large enough, I just mean that this index is larger than n plus 1, is at least n plus 1, and I have something that is larger than the previous element. Then by construction, this set B is a subset of A because all these capital B's were subsets of A, and I'm just taking some of their elements. This is infinite because this is an inductive procedure that produces a sequence. And more than that, what I get here has the following property. If I take any subset B prime of B, then it will differ from all these sets. This is not hard to see, you just need to think for a minute. So that's why this blue star. But this means that we are not in F. However, by the corollary from the previous slide, there exists an infinite set B prime sitting in B such that the characteristic function of B prime belongs to the subshift of primes. So this means that the B prime is in F, but this is a contradiction. So on one hand, this is not a member of F, and this their corollary means that it is a member of F. So this means that F must be uncountable. So what is missing? So I lied before a little bit. So what is missing to prove the uncountability of the subshift of primes is that we need to find this infinite p-admissible set A. But this is not so hard. So you can take the primorials. So you can produce this set A, and you can do this procedure to find uncountably many members of the subshift of primes. Okay, so let me stop here. Thank you.
Thank you very much. Questions?
Okay, so I have a following question. If you consider this density, in general, it isn't true that it always exists, yes? But my question is whether there is some merit in considering this in the sense of the generalized limit, something like a Banach limit or limit with respect to the ultrafilter. This one always exists, but I don't know whether you can extract any useful information from considering such quantities.
I never thought about this. So maybe there is some relation of what you are talking about and logarithmic density, but I don't know. I mean, this logarithmic density is useful enough and much easier to grasp than this density is defined via ultrafilters. That I don't know if anyone studied this. So sorry, I don't have a better answer.
Okay, thank you.
Any other questions or comments? Well, if not, maybe I will ask one. In your examples, B3 sets, do you consider, are there any examples of systems which have one invariant measure, which is supported by these sets?
Yes. So this is possible since the Mirsky measure is always the member of this set. You need your system to be uniquely ergodic. Also, there are some natural subsystems of the B3 subshift. So for example, if you have this B, you can always find a taut set B prime with the same Mirsky measure. This doesn't give you more invariant measures yet, but then you can go further to a further subshift. There is always a Teplitz subshift sitting there. The Teplitz subshift might be uniquely ergodic, it might not be uniquely ergodic. But what is interesting, this Teplitz subshift is also a B3 system. So you can have a B3 system that is uniquely ergodic. It must be Teplitz. But not every Teplitz B3 system is uniquely ergodic.
Thank you. Any other questions, comments? Maybe there's somebody from Zoom. Are you there? Do you listen? Any questions from Zoom? It appears not. Any other questions from audience? Well, if not, let's thank the speaker, Joanna, again. Thank you very much for your talk. Perhaps see you here sometime in person.
Thank you and goodbye.
Yeah, thank you.
Potem wracasz, tak? I pogadamy, tak? Dobra, to ja w sali B będę. Tak, jest.
Aha, tu jest.